Hello and welcome. I'm Yusuf Ali.
And I'm Moritz Löwenich.
We are both PhD students at the University of Duisburg-Essen under Hartmut Wiegers and Christoph Schulz. Today we are going to show you how we synthesize in our lab, mainly nanomaterials, and the future aspect.
Which is silicon nitride materials as an active material for the anode.
Then let's go. Hello. So this is the spray flame reactor where we synthesize our nanoparticles from LLGO to LATP. As you can see, this is a closed system, and here we synthesize our material, and here we collect the particles. Now from this side, I want to show how we prepare our precursors as well as how we synthesize here. Like every wet reaction, we also have solid precursors dissolved in one or more solvents. As you can see here, for LLGO, we have lithium, lanthanum, zirconium precursors that's generally dissolved in ethanol and hexanoic acid. And over here, we have the spray flame reaction. The reactor forms the pilot flame mixture of methane and oxygen. And here we have the precursor. It goes through here to fit in this reactor. And with the help of oxygen, it gets droplets. And that droplet makes the spray. That's why the name of the reactor is spray flame reactor. When the particles form here, they get quenched very fast with the help of water here and quench gas here. And then they go through upstream, and we collect these powders here in the filter. As you can guess, this spray flame reactor is a closed system, and generally we operate at a little bit low atmospheric pressure, and we have pressure sensor, temperature sensors, and to regulate the pressure we have the pump system, which is connected to a bigger pump. And from here you can see that this is a very well-defined system. You can control the gas flows as well as monitor the temperatures. And this is a system where we also can control what is the rate of precursor feeding into the reactor. With this lot of parameters, you can control which kind of materials you are going to get at the end. You must have noticed that this reactor can be upgraded to industrialized size, and everything can be automated. However, as you can see, we use this back filter here to get like 1 gram per hour, but we can upgrade this one to get more bigger filters to get up to 1 kilogram per hour, and it can be improved further. Now I transfer to my colleague Moritz for hot wall reactor.
Exactly. In the hot wall reactor, we produce mainly silicon-based materials from monosilane. This is a gaseous compound consisting mainly of silicon and hydrogen. So the process starts here at the gas bottle. And let's see the rest. The hot wall, or free space reactor, is generally a rather simple principle. First, the gases are introduced from the nozzle up here, and then introduced into the hot wall, where the monosilane is decomposed, forming the silicon particles. A precise control of the different flows is crucial here to obtain the desired materials, as well as to prevent wall depositions. The generated aerosol is then transported to the filter, where the particles are collected and can be automatically released by pressure surges or vibrations. And sometimes you have to help out manually as well. So with a double lock system, then the powder can be transferred to our glove box, where it can be collected inertly and without creating a mess. So, as you can see, working all day could be quite exhausting, but with our programmable logic controller, we have implemented a high degree of automation, so the system can run on its own and every data is locked. But of course, you can also steer everything by hand if necessary. With this equipment, we can produce highly specific nanopowders, in this case silicon nitride, at rates of up to 1 kilogram per hour. Silicon nitride has a very high lithium storage capacity in the anode. So at high production rates, we will need vials like this or even this. Our setup is already quite big for a university, and we could already gather experience from the comparison of this device to smaller hot wall reactors. Furthermore, we published an article about the successful upscaling of this process to an existing pilot plant in industry, capable of producing well into 2-digit tons per year. So regarding the production technology, we are talking about technology readiness level 8 here. For the specific material development, we are right now around 4 to 5. After synthesis, we analyze the obtained powders by elemental composition, thermal properties, structures, or also the ionic conductivity and optical properties. Also, we have a big microscopy center just below us. And in the end, of course, we're interested in the performance of our material in the battery.